Good morning. I'm Adam Post with the Indiana DOT. I'm going to first start off just by giving some INDOT's perspective on some of the bridge deck technologies that we've used, mainly the transparent stay-in-place forms, and then the internal cure and liquid fly ash, the E5 and the concrete and the bridge deck overlays, and then turn it over to David and Robert to talk more in specifics about their products. As far as the transparent stay-in-place deck forms, INDOT's relatively new in using these. We've used them in 3 locations across Indiana, one in LaPorte in the northwest part of the state, and then 2 in the Fort Wayne district, which is the northeast part of the state. We talked to the contractors. They seemed to like these after they got used to putting them on. They said they weren't any harder than the metal deck forms to put on. Our construction inspectors like them. Obviously, they can look below the deck and make sure the concrete's being consolidated around the reinforcing. Our bridge inspectors like them as well. They can rate the deck better. I know if you guys are inspectors out there, when you've got the metal deck forms, you can't really rate the bottom of the deck, so they like to be able to do that. And then our bridge asset engineers like to be able to see the condition of the deck as well and be able to determine the right treatment at the right time, whether it be a overlay or a deck replacement, instead of waiting until there's water and rust seepage through the stay-in-place forms. They can schedule the next treatment more appropriately. So we'd like to use them more often. We've been kind of picking the locations that we're using them now, but we definitely like what we see so far. As far as the E5 internal cure and liquid fly ash, INDOT's probably one of the front runners on using this. The product was actually invented in LaPel, Indiana. This slide's a few months old. We've probably upwards of 300 locations now between the full depth decks and the deck overlays. I actually took some of these slides from Mike Nelson, who presented at one of the monthly meetings last year. He's our concrete engineer expert. He's come up with a lot of the mix designs and the memos on this subject, so I actually included his information at the end of the slides if anybody wants to reach out to him and get in touch with him. So we're over 200 pours on our full depth decks, denoted by the black dots. We started off just using the curing compound. Now we're using plastic sheeting, and then the last 80 to 90 pours, which started last year, we're strictly using the E5 internally cured and liquid fly ash. Deck overlays, we've made some good progressions in those as well. We started off in 2020 with a few decks, had some minor cracks, but we've been very successful in the last couple years, and have done upwards of 50 of those, and we do still have the 7-day wet cure on the overlays. We haven't really given that up yet because the contractors haven't really been complaining about it, but we do put fibers in the deck as well, and have had good success with that. All these decks and overlays were done per the contractor's option based on a few of our construction memos, the newest one being 2301. I'm not going to read through all these benefits, but the main goal that we were trying to solve was the issues behind the screed when we came up with this mix design, or when we used this mix design, but we ended up correcting so much more than that and finding a lot more benefits when we used this mix design. We had improved workability. Obviously, we're getting rid of the evaporative retardants, minimal bleed rate, just a longer window for finishing, just more forgiving, a better consistency, and that it kind of makes the average contractors better. And we don't have the supply chain issues that we've had with some of the silica and some of the other pozzolans that we've had with some of our other mixes over the last couple years. As far as the hardened concrete, we have minimal to zero related cracking. We still have the cracking over the piers, but we don't have any of the plastic or shrinkage type cracks. Improved strength, excellent bonding on these overlays. Here's I-469 northbound overlay. We've got the E5 overlay. We actually did 2 different types on half the bridge. So the E5 was on the top part, and then silica fume was on the bottom, and you could see there The silica fume had cracks that started right away, whereas the E5 did not. This is another project, State Road 3. This is one of our earlier overlays. We actually had some cracking on both of these, but you can see on the silica fume on the left, the shadowing of the cracks. This is after a rainfall where the water is getting down into the cracks, whereas the E5, the cracks were so tight and we didn't have any of the water or moisture getting down into that deck. And we've taken cores. We've noted that the bond strength has been 2 to 2.5 times higher. But this is still a new product, going on 3 years, so we've only had a few freeze-thaw cycles. So we're still doing chloride testing. Purdue is testing daily on this material, and I think Robert's probably going to get into that a little bit as well. Some of the silica issues we've been having, where the undissolved bags are staying in the deck, and then you have pop-outs and some other issues that we're seeing. We're just not seeing that with the E5. It's resolving those mixing issues common with some of this bagged silica fume. And then our most recent memo has expanded the usage options for the E5, whereas before we were just using it in decks, slabs, and bridge approaches and overlays. We're opening it up to bridge and median railing, substructure, PCCP, curbs, sidewalks, a host of different options. This one was a E5 slipped railing. We actually had a contractor come to us last year because of some of the supply issues he was having getting the silica and the pozzolans, and requested to use the E5 on the slip form railing. And he had great success with it. We've now done this on around half dozen projects, and they're noting that they're probably having about a 20% increased production on using this. They're doing minimal finishing behind the machine. They're not really having to touch it at all. It looks better. They've been doing thousands of feet with this with no cracks. So that's pretty much all I have. I did include Mike Nelson's information on the last slide, and he said he's happy to take any questions, or if anybody wants to get in contact with him, he can give you some more information. And turn it over to David now to talk more about his project.
Thanks, Adam. Hey, good morning, everyone. I'm Dave Brodowski with TrueTech Bridge. I want to say thanks to the partnership for giving me the opportunity to present today. Also, thanks to South Dakota for hosting again. It's been a great meeting. So we've been talking a lot this week. I don't know if you sat in Dwayne's presentation yesterday about building a little bit differently for the future. You know, how do we build things now so that it lasts longer? And, you know, we look at a lot of things like deck forming. If you're building with lumber, going back and stripping it, is that lumber taking any moisture out of the concrete? How long should we keep those in place before we open it up? A lot of questions around that. Typically, if you're using corrugated metal pans, or those corrugations actually restrain the concrete and cause some of the cracking that we see from time to time. During placement, are we adding too much water? There's all sorts of things that can happen with trucks and delivery, and we're just kind of stuck with what we get at that time. And then curing and maturity. We're doing cylinders today, we're adding burlap, but there's a lot of new technologies and things that we can do today to help improve that process. And so that's what we're going to talk about today, are those types of technologies. Some states are having issues with early deck cracking, which hopefully we can start avoiding with some of these new technologies. Eventually things are going to crack, unfortunately. We talk about the preservation has a bridge deck preservation resource guide. 2 main points here. Number 1 is the bridge deck. If we keep it in good shape, it's acting like a roof, protecting all the other elements of the bridge. So we want to protect the deck for just the future of the bridge, right? The second is that construction quality is the most salient factor in long-term performance of that deck. So if we can build it right the first time, we're going to get longer life out of it. So what we're talking about today is the I-469 over Lafayette Center Road project. This is with Indiana DOT back in 2019. INDOT decided to use 3 different new technologies on a single bridge to help address some of those durability issues and things that they've been seeing. The first technology was clear cast forms, which I'll be talking about, and then Robert will come up and talk about the internal curing that was used, then also some sensor technology that was kind of at a demonstration stage, but definitely a cool thing that INDOT was looking into. So this bridge, it's a 3-span bulb T concrete girder bridge. It was built in 2 stages. I think the first was the spring of 2021, and the second was in the fall. So it's a 2-stage deck project. They use the transparent stay-in-place forms. As Adam said, they like this because you can inspect it during the placement of the concrete to confirm consolidation of the deck. Also, it eliminates the risk for falling for that contractor if they have to go up and strip forms. The contractors like using this over railroads or tall girders or over tall rivers just to prevent some of the risk involved with stripping forms. And then also, you can go back and do the routine inspections. These forms give about 75% transparency to the underside of the deck so that you can keep up on the condition and rate the bridge accurately. So here's a quick video of this project, a little bit of the installation of the first phase. Like I said, this project was I-469, so it was built in 2 stages. Traffic was still going. It was roughly 6,200 square feet of formwork total. Each form was 6 foot wide. They come in 4 foot lengths. They're about 4 inches deep. They install exactly like stay-in-place metal forms in terms of the support system, so contractors are familiar with how to do that. As Adam said, they go in just as fast as what contractors are used to, and then you can see what's happening underneath during the deck pour. Everything was top-down construction. We had skewed forms at the abutments, so these forms can be skewed to accommodate different bridge geometries. And it is interesting to be underneath the deck. You kind of get dizzy as you get spun around here, but to see the concrete placed and consolidated is a really cool thing if you ever get a chance or an opportunity to be around one of these bridge decks. So we talked with Keith Litton after this project. He's the asset management engineer for the Fort Wayne district. He had this to say about the use of the forms. We're currently doing another project in his district after this. He loves the fact that he can see the concrete during consolidation. That's probably the biggest benefit to him because some of the issues he's seen over time with poor concrete construction and having to go back, set up MOT, and fix a brand new bridge deck that wasn't poured properly. He also likes that he can go back and inspect the deck over time. We do see, this wasn't on this project, but in a different state, during the deck pour, the construction inspection engineer was able to go and look underneath the deck during the placement and saw voids. So these are 2 different bridges in Missouri. They identified the location. The concrete was still wet. They went back, vibrated it, hit that spot, and they didn't have an issue. So another benefit for using the transparent forms. So this is the 3rd project Indiana DOT has used to date. On this project, they didn't specify it, so it wasn't a change order. They worked it into the construction documents that the contractor could form and strip or use transparent forms. So it's kind of a competitive bid, our system versus the labor to go back, form, and strip. And this project was won by Milestone Construction, and he chose to use the transparent stay-in-place forms for this 4-stage bridge replacement, I-69 over the Salamone River. So with that, I'll hand it over to Robert Caballero with Specification Products.
Thank you, Dave. Good morning, everyone. Thanks for the opportunity to speak. Well, all that's left for me to talk about is this last couple technologies that were used by Indiana DOT. And, by the time that the I-469 bridge came into play, you see from Adam's slides, INDOT had been very familiar with and experienced with using the E5 internal cure product. These are nanosilica, colloidal silica products. Essentially, what's a nanometer? Take a meter, divide it by a billion. Take an inch, divide it by a million. These are grown silica particles that are put into suspension. They're functionalized, and they have particle sizes of between 1 and 100 nanometers. So these are particle sizes smaller than what we've previously put into concrete. Essentially, they were bolting on and using the E5 internal cure product, which controls the water and cures the concrete from the inside out. It's ultimately could be used as an alternative to lightweight aggregate, but over a couple years of using this, they had experienced a lot of benefits to the contractors, the ability to finish it behind the screed, as Adam had pointed out. It was about getting it placed better, right? Getting it placed faster, doing it without adding water and doing things that jeopardized the durability. And so they had seen a lot of benefits, right? The elimination or reduction of bleed water prevents the migration of that water to the surface, increasing the water to cement ratio and lowering the durability on the surface, right? That prevents those migratory paths from being there after the concrete hardens, which allow pathways for moisture and other things to climb or travel into the concrete and cause deleterious effects to the concrete matrix and the steel. So they had seen benefits of reduced shrinkage, reduced cracking, and they had experienced the benefits on the job with accelerating the construction schedule, right? We're saving water. And so this I-469 bridge project was the first opportunity when they were going to employ the E5 liquid fly ash product too. This is a liquid supplementary cementitious material that essentially consumes calcium hydroxide to form more calcium silicate hydrate. When you do that, you can use this product to optimize mixes. You can use it to lower cement content. Varies depending upon if it's a 1L or a 1 cement, what regional chemistry it is. You can use it to remove supplementary cementitious materials. So you lose a lot of loads, you have inconsistencies due to LOIs, you have trouble sourcing fly ash, things like that. You don't have a second silo at a remote plant. This is a liquid supplementary cementitious. No influence on air content, no lost loads, repeatable, available, delivered readily, reduces permeability. When we combine the two of these, we're able to use the liquid fly ash to optimize the mix and use the internal cure to improve the properties and the placement, the construction schedule. So what you can see here is that the lab work done initially took the Indiana bridge mix from a 658 type 1 with 20 pounds of microsilica and a 0.42 water to cement ratio. When you consume the water to hydrate more cement, we see about 30% more cement hydration. When you do that, it doesn't travel upward. So you can use more water to hydrate the cement and get those properties that you need without forcing it through chemical, right? We're consuming the water, we're not allowing it to degrade the durability. So we can use more water in our mixes and use less chemical. When you do that, that lowers the influence on slump loss, working time, things like that, because it's not produced by a chemical reaction, it's produced by hydration. And so what we were able to do was remove the microsilica, drop the cement 12%, so remove 15% total cementitious, and we increased the water to cement to a 0.47. A lot of times with nanoparticles, we see strength. Sometimes we don't. And if it's a 1L versus a 1 or a 1.2, we see differences in the improvement to compressive strength. And so here we saw a very negligible improvement of 6% to the compressive strength. I'd call that the same strength. But we saw the flexural strength jump quite significantly, almost double. And so we were a little nervous that that might have created a brittle scenario or some material out there that might not have been durable. So when we use the ACPA calculations, both conservative and less conservative, to estimate modulus of rupture based on actual compressive strength, you can see that the actual flexural strength was still far above the rest. Look at how many aggregate fractures there are in this 24-hour flex beam. Usually you hear a fizzle and you have a lot of hot solid rock that pulls out of the aggregate unless you have a high early strength with a flex. So we weren't sure what was going on here, so we pulled cores. We sent them to Dr. Luna Liu at Purdue University. And Dr. Liu and Dr. Weiss have been testing this stuff for years and have a lot of great data and great support for it. So cores were pulled, sent to Luna, and basically she points to the 3 phases of concrete, right? In school, we learn about the mortar fraction and the aggregate fraction, and you learn about the interfacial transition zone, but she points to this as a phase of concrete because there's an excess of moisture and calcium hydroxide at that interface around the aggregate. And so what you can see is that that influences the paste to aggregate bond, okay? And so that higher water to cement ratio and calcium hydroxide forms this weakest link in concrete. That's why we see a lot of failures of that paste to aggregate bond. And so Luna said, don't worry about it, you guys are all good. The thing is, your nanoparticles are anionic. They're very small. They're attracted to water. They consume calcium hydroxide. So what you have here is when you look at this diagram of the aggregate particle, the space to get up into the ITZ is on average about 40 micron. When cement gets wet and it's being mixed, it establishes this bulk packing phenomenon that won't let it get in there to the ITZ. Well, nanoparticles are small, and nanosilica is 100 nanometers or less, and it likes water, and it consumes calcium hydroxide to form more calcium silicate hydrate, enhancing the interfacial transition zone. Just the creamy nature alone of the mix that's provided by the E5 internal cure products. You can see on the right how much more cohesive and uniform that bond is of the aggregate to the paste versus the same mix without those products. It makes sense that that aggregate would not be holding. When you improve the ITZ, you do a lot beyond enhancing the aggregate bond, right? You improve abrasion resistance, right? You improve concrete ductility, and you reduce micro cracking. Those cracks you see that are macro cracks, micro cracks, they're nano cracks when they start. They're much smaller than that before you can even see them with water. Some pictures from the job, right? This makes the mix very friendly. It was developed for contractors. It was developed to make it easier for them to place good mixes, for it to last a long time, get closed up well, and be durable. So the customers didn't have a problem with it long term. So over here on the right, these guys you see relaxing, they'd normally be throwing the water on the surface, right? They'd normally be putting the hole in the water bottle, squirting it out there and finishing it in there to do us a good job with color and durability and all these things that we need for long-term service life. So we don't like to show that guys are relaxing out here, but that's what this creates, longer working life. INDOT does not allow water added to the surface, none. They can use a higher water to cement ratio. They don't have to use a mid-range because this gives you those fresh properties using water, right? Picture of the hardened deck. Some sensors that were used, basically the Geotech Smart Rock maturity sensors were used. We're all familiar with those. You do lab testing. You establish a maturity curve for temperature versus strength. And instead of using companion cylinders, which aren't as representative, you monitor some in situ temperature curves or temperatures using Smart Rock maturity sensors, and you identify strength, and then you can hit it without relying on the lab to give you those breaks. Dr. Luna Liu's been developing these Rebel sensors, and they were much earlier on when this started. That's the new one up top. The one in the bottom that looks like a puck is that one. And she was doing developmental work, so we were not super involved with this. We didn't get the data for it, and she has done a lot more development. But the advantage of her piezoelectric sensor is that it measures direct in situ stiffness and correlates that to compressive strength in real time. There is no lab testing that's necessary. There's no maturity curve. There's none of that, right? So it's a big jump on the maturity sensor. So what did we accomplish? Well, when you remove wet cure, 7-day wet cure, you save about 0.6 gallons of water per square foot. That's 8,300 gallons of water. That's enough for 100 people for a day. We saved $16,000 because it was $35 cheaper per yard. And we saved time, 7 days less of cure time, accelerated installation and finishing. Transportation of the cement, the microsilica, the water, all that has a carbon footprint. Materials alone, we saved about 21.5 tons of CO2. There's more involved there with transportation. Remember, INDOT started this to help behind the screed for the contractors, and they discovered so much more, right? You've got to listen to your contractors. Let them tell you what they need, and sometimes they can drop something in your lap that will help bridge preservation. We're talking about preserving things that are in place, not falling down. Let's do things for our kids. Let's not put them in the same room in 50 years trying to solve the same problems we are. Use these new technologies that are available. They can do a lot for you.
So, yeah, we do have some time for questions because somebody didn't get approval to do a presentation at the end of today.
That
Yeah.
one was going to get rolled into.
Okay. All right. Well, do we have any questions?
All the way.
So I'm going to back away. You guys can respond. Good job. Good job. Good job.
Okay, good morning, everybody. Okay, you did mention about the transition zone where the fly ash tend to reach just between the coarse aggregate and the cement paste, right?
Interfacial transition zone, yes, sir.
Yes. And you introduced fly ash, but I don't know in your research what kind of cement did you guys use? Because in that region also you got to be careful that there is something called, maybe people might have heard of it, of course ASR, alkaline silica reaction, and there's another one that tend to involve with the sulfur 4 oxide, which is ettringite, which people much don't know of, is on early curing. When you cure it too fast, you might introduce those. And you did mention also saying that the microcracks tend to be where it is, and then it starts develop to macrocracks or whatever it goes to. So I don't know how long you guys did this, or did you guys have any research data to back it up, whether that was...
Yes, sir. Yes, sir, absolutely. I appreciate the question. The interfacial transition zone, that comment about the reaction was just, this was a type, where was the mix? This was a type 1 cement with 20%, with 20 pounds of microsilica. Then we ultimately removed the microsilica. And when we were talking about the interfacial transition zone, it's just about the nanoparticles. It wasn't about anything to do with the fly ash. This is a straight cement mix. But bulk cement, when it's wet, has that bulk packing phenomenon, and it doesn't allow it to get between that 30 to 50 micron space that's really what accesses into the interfacial transition zone. But the nanoparticles, which are less than 100 nanometers, they can weave in there, and they're pulled in there because they're attracted to the water. Once they get in there, they consume calcium hydroxide. They form more calcium silica hydrate around the paste to aggregate bond, which is what gives us that kind of more robust hardened matrix that we see. I've got white papers, I've got Purdue research for several years. INDOT has done countless placements and work. If you'd like to talk, I can share, plenty of data, any support that you'd like to see, happy to have a conversation. Okay, thanks for the question.
Let's give him a round of applause.